Okay, do you see the screen?
Yes, Hocam.
Okay. So we were talking about multivibrators, and we said one of the multivibrator type is the one that can be obtained with back-to-back two inverter. You know, with this multivibrator, if the input is 0, output 1 will be high, and output 2 is going to be low, which is already connected to input. So it can either stay at low at the input, it will keep and store its value, or if we set input as 5, then once it's set, it's going to be stable at that number, and then 5 volt, output 1 will be 0 volt, and output 2 is going to be again 5 volt. So, and then the concept is explained with this, with the graph in here with output 1, output 2, and input versus output 2, which is equal anyway, you know. And then we can see that there are 2 or 3 cross-section points, but one of them, the middle one, is unstable state, so it's not going to be staying in there. So we said that this concept is used to make the first maybe latch, which is called SR latch or memory unit, SR flip-flop, maybe we can call it. And you know, this is kind of a memory element, and in this memory element, you know, if we think that these are the inverters are implemented with your some NOR gates, you know, but then utilizing one of the inputs of the NOR gates, then we can have an output. You remember NOR function? What was NOR function? You know, if you have AB and NOR output, I mean, if it is 0, 0, output is going to be OR is going to be 0, NOR is going to be 1, 0, 1 is going to be 0, 1, 0 is going to be 0, 1, 1 is going to be 0, right? So this is the function. So what we achieve here is, you know, with the SR flip-flop. So if you remember, maybe you just started to learn, or maybe you learned it already, but your next state data, and then next state Qn plus 1 bar. So this is going to be Q, and then this is going to be Q bar. And here I can say that the R output is Q, and then this is going to be Q bar. So the value here is like that. Like if you have 0 and reset is 0, so there is no reset or set. So the data in here is going to be the previous data. What is previous data? We call it N. Okay, so this is going to be Qn bar. So how can I show it here? So if, let's say, this data was here, let's say reset is 0. Okay, reset is 0. And then this is also 0. So if Q was 1, so then this would be 1, and then this would be 1. What would be the value of here? 1, 0 makes it 0, right? So this would be 0. If this is 0 and then this is 0, this is going to be 1. So the data is going to be stored, the previous data. It's going to be always like this. Okay. So if the data was, let's say, another value, we are talking about 0, 0 case. If this was 1, then this would be 0. If this is 0, then this is 0, the other one. Now this is going to be 0, 0, it's going to be 1. So if this is 1, it's going to be 1 again. Okay, so for the two cases, as we see, the stored data is, kept. This is also valid from here. If the reset and set are set to 0, they will be acting like an inverter, two back-to-back inverter. So if you have one of them is 0, this is also an inverter, right? So if this was 0, this was going to be like this case. So this is equal to this one. So the stored data is kept. But by putting reset and set gives us the option of maybe the option of setting or resetting. So if we have the reset entered here, so reset is 1 and this one is 0. Okay, set is 0. What happens? If reset is 1, no matter what, Q is going to be 0. Okay, no matter what. Why? Because if one of them is 1, output is going to be 0. So, and then naturally, if that's the case, Q is 0, and then set is 0, so output is going to be 1. So this is what happens. If the reset comes, Qn becomes 0 because it's reset. Okay, so the other option, maybe I can do these with different colors so it will be easier to differentiate. If set is 1 and this one is 0, then what happens? The set is 1, this one is 0, then for sure, since set is 1, Q bar is going to be 0. If Q bar is 0, this is going to be 0. And then if the Q bar is 0, this is 0. And then this one is 0. 0, 0 becomes 1 here. So therefore, this becomes 1. So therefore, we can either set or reset or keep this as a memory. This option of putting 1 and 1, we don't want to set 1 and reset at the same time. So this is not used. Not used, okay? Why not? We don't need to set and reset at the same time. So what happens if we use it? Yeah, you won't burn the circuit, but if you put both of them 1, both Q and Q bar is going to be 0, which is nonsense, okay? So if you use this, if used both Q and Q bar, will be 0, which is meaningless, right? I mean, so, and then when you go back to 0, 0, you don't know which one is going to win, you know, that battle. And then you don't know what the output is going to be, undetermined. Will be 0, okay? So that's kind of it. I mean, we learned first, what did we learn? We learned that this is a bistable circuit, okay? And then bistable, we can use it it is also a bistable circuit which can be used as memory, as a memory element. Okay, another usage of that, we can add set and reset functions. Okay, so this is also equal to, let's say, ground. Same thing, right? They are all same. I hope this is clear. I mean, so if you remember last time, we have seen another way of implementing this bistable circuit using what we call as a Schmidt trigger. Okay, this was an interesting element. And then, we could use that bistable circuit. So now we will see another interesting circuit. Now, in this circuit, we use some, again, like these, what is it called? What is it called? Maybe inverters or NOR gates, NAND gates. Actually, we have NOR gate here. And what the this can be considered as a CMOS gate, and then we can say that when the input is VDD divided by 2, and then this becomes VDD divided by 2 until that time. So we can consider this as an ideal inverter. Okay, so this is CMOS. CMOS circuit gate, CMOS gate, with the following ideal response. Okay, we know that the actual response is like this, right? I mean, this is like the actual response. And this one is ideal. So, this circuit, we said it's going to be monostable multivibrator. So monostable, why do we say it's monostable? Because if the input, this input, when it is 0 initially, the signal will be stable and V out is going to be remaining at a certain value. So, for this circuit, the input, what happens if the input is 0? Okay, so if the input is 0, we can find all the other values here. How can we find that? We can start with putting a 0 here, and then saying that 0 here, and saying that the circuit was remaining in there for a long time. Okay, so steady state almost, right? Okay, so long time in here, okay, at 0. So we say this is going to be a long time. Why? Because we want to determine the value of V out for that long time waiting. How can we determine that? There's a capacitor here, resistor here. So we know that when t, let's say this is t is equal to 0, okay? T below 0, the circuit at steady state. At steady state. That means the capacitors are capacitor has no current. Has no current through it. Capacitor has no current through. Okay, it's steady state. So the current is 0. So if the current is 0 and this is CMOS, then the current here is going to be 0. And this current is 0. So the resistor, let's say this current, IR is going to be 0. So if that's the case, then what is the value of V in 2? You need to tell me this.
VDD?
Yes, VDD. Okay, because there's no voltage drop, so it's going to be VDD. So V in 2, we found out that it's going to be at VDD. So let's draw it here. So it has been sitting here at VDD. We are trying to find all the values here. So if V in 2 is VDD, what is V out? You need to tell me.
0.
Yes, 0. Okay, so we found V out. Wow, good. 0. Let's find the other values because you know, this is going to be VDD, this is going to be 0, and then this is 0 and 0. Both of them are 0. Then what is V out 1?
VDD?
Yes, VDD, great. VO1 is going to VDD. So let's draw that also. So this is VDD. This is like a puzzle, right? Okay, so what about the capacitor voltage, VC? You know, this side is VDD, this side is VDD. What is capacitor voltage?
0.
Great. Okay. So the circuit, we found all the values here. And then this is, everybody is happy. Okay. So now this is a stable state. Okay, stable state. V out is equal to 0, then VO1 is equal to VDD. If that's the case, VC is equal to 0 volts. Okay, so everybody is happy. The circuit is steady state. Okay, So steady state. I don't want to write it again. So what happens? Then you might have a disturbance here, okay? At 0 plus, so this is, you know, so VC of 0, that means is 0 volt. VC 0 minus is equal to 0 volts, right? So that's also, we can call it this way. Because we know that at 0 plus, the capacitor voltage will not change. So what happens after this? After this, let's write maybe with a different color to you know, to identify this. After that, there is a trigger comes. A short trigger happens here, okay? So V in becomes VDD and then goes back to 0. Okay. So, and then the period here should be long enough, but not too long. Okay, so let's call it delta T for a period of testing. So T trigger. I don't know, can you read it? Okay. Trigger signal comes in here. So if that signal at T is equal to 0 plus, okay, V in 0 plus becomes what? Is VDD, okay? If that becomes VDD, what happens to our VO1? Okay, so this is VDD. This becomes what? VDD becomes
0.
0. Yes. So this becomes 0. So VO1 goes to 0. So let's draw that. And this goes to 0. Okay. If that one goes to 0, and we know that V in 2, which is equal to VO1 plus VC, what is that value then? Because capacitor doesn't change its voltage. So
0.
Yes. So let's say VC VC 0 plus. So this is 0. This is 0. So it's going to be 0. So V in 2 becomes 0 also. Okay. So this is interesting. I mean, we will see that the signals are now going to be changing, and due to that change, there will be some activity. Then if V in 2 becomes 0 now, right? This was 0. This became 0. What is V out? What happens to V out?
VDD.
Yes, great. VDD. So the V output goes to VDD. Okay, VDD. Okay, so the capacitor remains at 0, so it doesn't change initially. So if V out becomes VDD, okay, now this side is VDD. What happens? Now I mean, we know that this side is 0, this side is 0. Okay. So the capacitor will be charged through here now, because, you know, there is a current path here. Okay. I mean, this is 0 by the circuit forces. Okay. But here, this 0, capacitor determines. VC determines. Okay. Therefore, capacitor can be charged through R. So in fact, I mean, we will see that the capacitor will be trying to charge through VDD. Maybe I should draw this a little bit better, because we will be making a change here. So let's say this is VDD, and this is half VDD. So the capacitor will be trying to charge through here. Okay. So the critical thing here is when the capacitor voltage becomes VDD divided by 2. So this is going to be charging with a tau value. Okay. So the capacitor, we see starts charging through R. Okay. Wants to go to VDD. Okay, so that's the goal of the capacitor. Meanwhile, okay, at this point, at this condition, okay, even if V in goes back to 0, V out 1 will remain at 0 Why? Because V out, I mean, this is now VDD. Remains at VDD, or remains at 0, because, and it will remain at 0 until it changes. Maybe I should erase this thing, not because, as long as remains at VDD. So, you know, V into starts increasing. Okay. So V in 2 starts increasing. Okay. And V out will change, will switch back to 0 when V2 reaches to VDD divided by 2. Okay, so that means, remember V2 was equal to here, like this one, okay? So this will be until it goes to VDD divided by 2. Like this is VDD divided by 2. Maybe I should get this a little bit up. VDD here. Okay. So this is VDD divided by 2. Until that time where the capacitor is, because VC is added to VO1 and VO1 is remaining at 0. Okay, remaining at 0. So VO1 will switch when Vout switches. Meanwhile, this will remain at here. Okay, so until this time, which we can call it as Tx, okay, until that time, things will be like this, okay, but we have to be maybe careful here because this will not reach to VDD. Because when the time becomes Tx, Vn2 reaches here, Vn2 reaches to this value, okay? Then after that value, Vout changes. After that value, maybe I should select another color here. Then after this value, Vout switches back to 0. Is that clear why the output switches? Because this Vn2 input becomes VDD over VDD divided by 2, and this becomes 0. Okay, because it was 0, I mean, it used to be VDD, and then 0, now it's increasing, and then, when it reaches to VDD divided by 2, it switches. Is that clear? So that means the capacitor now will change its position. Or target of the capacitor will change. So this time, there is no trigger. So this is at 0. This is at 0. Now this became 0. What happens to V output 1? Becomes VDD again. So V output 1 goes back to VDD. Okay. If that one goes to VDD, what happens to Vn2? Now VN2 is very interesting because capacitor voltage doesn't change its value. Okay. Then V out becomes 0. Okay. When this becomes 0, V in went back to 0. VO1 becomes VDD. Okay. So V into, which is equal to V out 1 at Tx plus Vc Tx plus, it becomes what? VDD plus VDD divided by 2, which is going to be 3 VDD divided by 2. So V into really jumps like up to here. And this value is going to be 7.5 volts. 3 VC VDD divided by 2. Okay. And it's interesting. And then V into supports that V out, which is supposed to be 0 anyway. And then what happens? Out 1 remains here. After this, then capacitor VC starts discharging through R again until IC is 0. And then at this time, again, the V into EE until VC becomes 0 volt again. Why? Because V into becomes VDD. Maybe I should say not like this, until V into capacitor is 0 until V into is VDD. So VC becomes 0. Okay. So the capacitor will start discharging again. Okay, so with a time constant of tau. Okay, and then that means this will be going back to this voltage. Okay. And then it will remain in there. And then this will be continuing like this. And then this will be continuing like this. Sorry, this was too tight, you know, to complete. But I don't know, I guess I managed. Maybe with the colors, it helps. Now, did you understand what happened as a concept?
Yes, hocam.
Okay, the concept is that this was steady state, a stable state. And then we got a disturbance. Okay. And then the disturbance created the signal Vout, fixed period. Okay, for a fixed period. And we can calculate that fixed period value, by the way, from the capacitor. And then stable state again. Okay. So this is the concept. So how can we find the value of Tx? You know, capacitor is charging here. You know, this charging we know, and then initial value of VC initial. I mean, let's calculate it here. VC of T is going to be equal to what? V final plus V initial minus V final, e to the power minus t divided by tau. Okay. So V final, we know it's VC of t. It's equal to VDD, V final. V initial was 0. So minus VDD e to the power minus t over tau. And we know that VC at t of x, which is going to VDD divided by 2. So from here, VDD minus VDD e to the power minus tx divided by tau. And then from here, you can find that tx is equal to tau times ln 2, or r times c times ln 2. So that small disturbance causes and triggered output, okay, for a fixed period of time, Tx. So as I told you, like you can use this as an alarm. Let's say somebody tried to open the car door and then forced it, and then that shaking, you know, can start a disturbance, a trigger, V in, and then even you stop, you know, shaking the door, let's say, or the thief stops shaking the door, still alarm will go off for a while, and then maybe 1 minute later, 30 seconds later, whatever, you know, you set it up with an RC value, then it's going to give you an alarm for a fixed period of time. So until the next disturbance comes, the circuit will stay at its steady state. Okay, monostable. Is that clear? I tried to make it a little bit clearer with the color pens, and I hope it is useful to identify different states. You know, there is one other thing that has to be, you know, mentioned here at least. But I don't know where to put that value. This is so tight here. I should have used one extra slide here. Let me use maybe insert a sticker. You know, there was a way to insert a sticker. Was this the one? Is this the sticker? Sticker? What is that? Something else. That's for cutting. Anyway, I forgot. Let me do this. Okay, maybe I will do this so that hopefully will be clear. So one just little thing is that any CMOS inverter has protection diodes. So you need to know about this. Let me, you know, put it here, maybe. Okay, let me write it first like this. You know, if you think about a CMOS inverter, this is how you implement, right? So typically, in the CMOS inverter, this is VDD, and this is VIN. There are these protection diodes. So the protection diodes limit the voltage VIN is limited between 5.7 volts minus 0.7 volts. Limit VIN, okay? So, you know, there is as if you have here some kind of diode. Okay, protection diode. So due to that protection diode, the voltage here cannot reach to VDD. So this goes up to here. And then this goes like that. So the capacitor is okay, but this one goes like that, okay? Due to the protection diode, VN2 can reach to 5.7 volt only. So the capacitor discharges very fast. So the capacitor jumps down here and then, already 0.7, is going to be like this, okay? So the capacitor discharges through the protection diode. Okay. So this is maybe a small detail, but I mean, every year we warn the students, when you have something like this, if you want to try this in your lab and then verify this in the laboratory, you will be noting that that voltage doesn't jump to 7.5 volts. It can jump only 5.7 volts. And that's the reason. I mean, don't be surprised if you see that. So that's the reason I talked about it, and we have to talk about it, okay? So is that clear? Since the capacitor, when it turns on, the resistance of the capacitor is much smaller, it discharges very quickly through the diode there. The diode. Okay, so shall we give a break or? Or maybe we can cover one more circuit and then finish for today. But the next circuit will not be analyzed in details like this. What do you say? Shall we give a little bit break? Or you want to just go to the next circuit and we talk about it, not solve it, and then finish for today? No response. So let me then just go through another circuit here. This looks a very simple circuit, but this is something totally different. Astable multivibrator. What does that mean, astable? The circuit will not be stable. It will go high and low and high and low and high and low all the time. I know you are tired, but let me at least, start, maybe give you some, go ahead, and then you can do this yourself. Now, here, let's assume again, like this one is ideal inverter. I mean, ideal CMOS inverter doesn't mean this, but you know, let's just for simplicity say that the response of the circuit is like this: VDD divided by 2, and this is VDD. Okay, so the signal changes rapidly here, very rapidly here. Okay, so for a circuit like this, you know, analysis is going to be a little bit difficult, but you might want to start with some assumption. So in the previous case, we assumed that the capacitor was empty. So you can start with that assumption. So what happens if the capacitor is empty first? So we start with red light here, right? So let's say that initially capacitor is, let's say, at 0 volts. VC at 0 is equal to 0 volts. Okay. So so what happens if that is 0 and then no current is passing from the capacitor? And that means, you know, here is ideal. So the current is equal to 0. So here is 0 current. I is equal to 0. So therefore, the voltage here, or the yeah. So I guess we need to make an assumption in at a certain point. So yeah, V in 1 will be equal to V in 3 because this is 0 volts. This is 0 volts and then connected. So as if it is the stored value. So we need to make an assumption. I mean, is V in going to be 0 or another value? So let's assume that this is also like 0, because if this is 0 and this is 0, everything is consistent, right? And then this is going to be VDD. So V in 1 is going to be 0. Capacitor is 0. Let's say this is V2, which is going to be VDD initially. And then V3 is going to be 0 initially. So this is like the initial cases. So what happens if this is VDD, this is 0, and then this voltage is forced? This is forced by the inverter. So this voltage, however, is generated by, so this V1 is equal to V3 plus V collector voltage. So, you know, when you have this kind of circuit, you know, now there's going to be a current through the capacitor, because capacitor wants to go to which voltage? What is the goal of the capacitor?
VDD.
No. Yeah, one side is VDD, one side is 0. So, I mean, this is 0 initially, but then it wants to be stable. So it wants to go to VDD. So the goal of the capacitor then is, maybe I should select this. What did I choose here? Green. So capacitor wants to go to VDD. So the goal of the capacitor is to reach to VDD. However, while this is happening, what is the value of V1? You know, if the capacitor wants to go to VDD, V1 wants to go to VDD. Why? Because V1 is equal to V3 plus V capacitor. V3 was 0. So V3 was 0 here. So, but things will change. So maybe I should have, you know, drawn this a little bit better. I should do this here. Here, things will change. So it starts like from here and then wants to go to VDD. And this one, if this is VDD, this one wants to go to VDD. So it's going to start like this. And the goal is to go to VDD. Okay. But when this thing comes to VDD divided by 2, and when this becomes VDD divided by 2, in fact, inverter 1, this is inverter 1, inverter 2, okay, inverter 1 will switch its state. Okay, so this will continue, but here, inverter 1 will switch its state, so VR2 or V2 becomes 0. Is that clear? So this remains in here. So if that's the case, then this becomes until VDD divided by 2. Okay, so we start from, this one starts from 0, it goes to VDD divided by 2. And then V2 becomes 0. If V2 becomes 0, the capacitor voltage was how much? VDD divided by 0. So what happens to, why did I get confused? This became VDD divided by 2. And then, you know, it goes to that value. And when it reaches to that, maybe it will be switching to here. This goes back to here. VO2 becomes like this. So when VO2 becomes 0, VO3 becomes high. Okay. And then VO3, V1 becomes what? Capacitor plus VC3, V3, V1 becomes again like this one. So let's say we don't have the ideal thing here. So this goes to 3 VDD divided by 2. Jumps to that. And then again, the capacitor tries to, go to a different value. The capacitor tries to go to this time minus VCC, minus VDD, sorry. And then, this will go to here. So in any case, you will be seeing that this will be switching here, and then until this becomes minus VDD divided by 2. So maybe I shouldn't have this. This is VDD minus VDD. So things will be changing again. So then it's going to be like this. So this will be keep switching back and forth. Okay. So you need to, if you calculate this, and you will be seeing that this is going to be a clock. So this is maybe T divided by 2. Okay. So you can calculate these times and then say that this is now an astable multivibrator. Okay. So you can calculate T1, T2, T3. Okay. Please calculate T1, T2, T3, and T4 maybe, I don't know, no need maybe. You will see that it's repetition. As an exercise. So, the idea here is again to make a circuit this time to give us a square wave generator. Okay, this can be used as a okay, and then the timing is determined by RNC. Or F, okay, which is equal to 1/T. Is that okay? So I think this was a heavy course today, but I mean, these are the two important circuits. And next time, we will see how we can generate maybe square wave, like similar to what we have seen here, with the other circuits. I mean, this circuit that we have, used for bistable circuits or for making some other interesting things here, okay, in the past. So again, the concept is to charge and discharge a capacitor and then make it so that it will be always going high to low, low to high, high to low, all the time. And Vy is going to be starting from 0. Maybe it will go high. Next time it will go to, minus Vy, V1, and then it will be going up to here, down to here. Okay, so why or how? We will be analyzing it maybe next time. Is that okay?
Yes.
Okay, I'll be stopping here. And then if you have other questions or any question about this, I can answer, try to answer at least.